In the last lesson, we looked at standing waves on a string, which exemplify stringed instruments and how they work, whether we have the first harmonic or second harmonic or third harmonic, and how that's based on the length of the string, right? And the standing wave that you can put on that string. So today we're going to talk about air columns, which is most useful in thinking about how sounds come out of a column when air is put through them. So for example, something like a clarinet or a flute or any of those woodwind band instruments, those are all either open or closed air columns, and you get different sounds out of them based off the fact of whether they're open or closed. Obviously, there's a lot more than the sound than just being open or closed, but that's kind of one of the most basic things, and at least what we're going to go over in physics. Okay, so when sound waves form in a column, like a wind instrument, the sound waves are going to form points of constructive and destructive interference. So what's happening is that the air inside the column is resonating. Okay, it's not like the actual, like what the air column's made out of is resonating, but the air inside the column is resonating and producing those standing waves, okay? So of course we're going to start with closed air columns. So this is like a clarinet where it's almost fully closed at one end, but it's fully open at the other, okay? So when you have a closed at one end, but it's open at the other end, you always need to have a node at the closed end, and you always need to have an antinode at an open end. Okay, and so because of this only produces odd harmonics. You're going, okay, why? Because again, if I need to have at a closed end, I always need to have a node at a closed end, and an open end, you need to have an antinode. This is the only way we can make these resonate, okay? And this is how they'll always resonate. Because if we had an antinode at an open end, that would mean it's making no sound, right? So of course, when we have our antinodes, that's when we have the loudest sound. So we need our antinodes at the end of the instrument. And this is just the way it works. So since there's always a node at the closed end and an antinode at the open end, then our sound waves have to be drawn like this, right? The waves going inside, like there's no way to have, so we have a quarter of a wavelength and we have 3/4 of the wavelength, but there's no way to have a half with a closed airway or with a closed end, because we need a node to happen, and a half of a wavelength would need to have an open end at both ends. So we can't have that. So in this case, when we need to have a node at one end and an open antinode at the other end, then we can only have quarters of wavelengths. We can't have halves, right? You're going, what are you talking about? The next one, you know, if you have 1/4 and 3/4, the next one would be 2/4. Guess what? 2/4 is a half. So we can't have halves. We can just have, or wholes, we can just have quarters of wavelengths when we're talking about closed air columns, okay? So so for example, of course, this is a quarter of a wavelength. Oh, if I can get this darn thing. Okay, there we go. So here we go. This is our quarter of a wavelength right there, right? Because that's really only a full wavelength goes, if you start at the node, goes up and down and back up like that, right? This is really only showing us that bit of that wave. So that is definitely just a quarter of the wave, okay? And then of course we have 3/4 of the wave, the next one, because here's one full half. And that's exactly why we can't have halves, because half of a wave where one starts at a node, then if you look at the next half, it'll have to be a node. And of course we know we can only have antinodes at the open end. So there's a full half right there, and then we have this extra little quarter. So that's 3/4, okay? 5/4 is just really 1 1/4. So if we look at this, we have one full wavelength right there, and then we have this extra little half. So that's what 5/4 is. It's really 1 1/4, and then of course 7/4, which is 1 3/4. So if we look, we have one full wave right there, and then we have 3/4 of a wave right there, which gets us 7/4. Okay, so you can probably see that the next one would be 2 1/4, then 2 3/4, then 3 1/4, then 3 3/4, and so on and so forth, right? And that means that our harmonics will happen when we have 1/4 of a wavelength, 3/4, 5/4, 7/4, 9/4, 11/4, so on and so forth. And that's how that's going to go. So let's go over some of the equations that we can use for closed air columns. Again, these are ones that you can probably come up with on your own. I'm not going to give you these specific formulas. I'm going to make a more general form of the formula, and then we'll give those to you on an exam. But let's look at just the specific formulas for like length and wavelength and the frequency for each of these, okay? So if we're at the first harmonic, then the length of the air column, because that's what we're looking at. This is the length, right? From here to here, that's the length of the air column. That's what I'm talking about when I say L there. That's the length of the air column. It's 1/4 of a wavelength, right? Because this is 1/4 of a wavelength. So we know the length is equal to 1/4 of the wavelength, which then means if we want the wavelength, then we can take the length of the air column, multiply by 4, right? And then furthermore, we know what frequency is equal to velocity over wavelength, but here we know wavelength is 4 times the length of the thing, so it's velocity over 4L, or velocity over wavelength, right? Because we know from our fundamental wave equation, velocity is equal to frequency times the wavelength. Okay, so let's look at this if we have our third harmonic, because we can only get the odd numbers here, right? We can get the first and then we can get the third harmonic. And really, how do we know it's the third harmonic? You know it doesn't look like it because there's only 1.5 standing waves, but if pretend that you were to finish this air pipe, then it would be that third harmonic. Oh, this is a horrible drawing, I'm sorry. But again, just visualize here. So here's our third harmonic, and so as we can see, the length of our air column is 3/4 of a wavelength, yes? So that's 3 times the wavelength divided by 4, which means that our wavelength is 4/3 of the length of the air column, which I know is kind of weird, but that's just how it works, okay? And then if we want to get our frequency there, again, we're at 3/4 of a wavelength, so therefore it's 3/4 of V divided by L, okay? And that's, again, just we know we have frequency is equal to velocity divided by wavelength, so you're just putting that in for wavelength. And instead of having velocity over 4/3 times the length, because fraction and a fraction, we rearrange things to get them looking much nicer, okay? And then next would be our fifth harmonic, because remember, it only happens at odd number harmonics. So here is our fifth harmonic. And again, if you just kind of assume that you finish off this air column, it's going to be nice and symmetrical, then we will have 5 standing waves there. Okay, so let's look at the length of this guy. Well, what was it again? There's 1 full wavelength plus another 1/4. Or like we said in the last one, there's 5/4 of a wavelength. So our length here is 5/4 of a wavelength, which means our wavelength is 4/5 of the length of the air column. Okay, so if we want our frequency, again, we take our new value for lambda, plug it in to V over lambda, and then we rearrange and we end up getting 5V over 4L. Are you noticing any sort of patterns here? Do you notice that the length is always divided by 4? Yeah, so there we go. The wavelength is always divided by the number harmonic it is. Okay, do we notice that the number harmonics shows up in the numerator of our frequency? So we are noticing some, by the way, this one's 1, we just don't write it, right? So we are noticing some patterns here. So let's go on to just some nice, consistent equations that can work for anything. Okay, that's what we're going to do now. So here are general formula. So the length of an closed air column, of course, this only works for closed air columns. So that's really important that you know that. This is the general formulas for closed air columns. So the length will always be n, the number harmonic, times the wavelength divided by 4. If you rearrange that, we found the wavelength will always be 4 times the length divided by the number harmonic, right? And 4 because these are always in quarters, these wavelengths, okay? And then our frequency, it was always n, the number harmonic, times the velocity of the wave divided by 4 times the length. Where again, we have this special thing happening where we know frequency for the nth harmonic is equal to n times the first frequency, or the fundamental frequency. So if I want the frequency for the 5th harmonic, I take the frequency for the 1st harmonic and multiply it by 5, okay? And we went over that in the last lesson as well. So those are some of your general formulas that you could be given for closed air columns, okay? So what makes the closed air columns unique and different from open air columns is closed air columns are always I was going to say being divided by 4s, but let's say always in quarters. So whenever you see the 4s in the equations, you know that you're dealing with closed air columns because we can only have the odd number of harmonics, which then eventually gives us quarters of wavelengths, okay? So that's how we know that those are going to be equations for closed air columns. Now, I'm going to go on to open air columns and what those guys look like. So this is when, of course, we know that what needs to be at the end of an open part of the air column. An antinode, we need to have this where we have an open wave at both ends. So if we have an open air column, therefore we need antinodes at both ends. And because we did this, now we can get halves of wavelengths, okay? Because again, I can't just end this column here where we have a quarter of a wavelength. It just doesn't work because it's open at both ends, and therefore there has to be antinodes at both ends, okay? So because of that, we get halves. So here we have a half of a wavelength, right? Because it's just kind of one going from the middle, the top to the middle bottom, but it's not a full up and down. Okay, so this is only 1/2 of a wavelength. This is one full wavelength because we start at the top and we go to the bottom, that's half, and then we go back up to the top, which is a full wavelength. This is 3 halves, which is really 1.5, right? So if we look, we go back up to the top here, so there's one full wavelength and another half. Here's 2 wavelengths. So if you start down here, you go up to the top, you go down to the bottom, there's one full one. Then I go back up to the top and go down to the bottom, there's 2. So in this case, we have halves of wavelengths. Of course, they just don't all look like halves because we don't call 2 halves, we call it 1, right? We don't call 4 halves, we call that 2 because 4 halves is 2, okay? So because of this though, this resonates at all harmonics. We have the 1st, 2nd, 3rd, 4th, 5th harmonic, okay? But we can still make this nice and general as well. But let's look at, again, some of the equations just for the specific situations. See if you can find any patterns, and then we'll go to getting our general equation. So here's your 1st harmonic, and that is where you have the least number of wavelengths as possible, which is half of a wavelength. So we know the length of the air column here is equal to half of the wavelength, okay? And that's just because that's the least amount of wavelengths I can draw with it still being open at both ends and therefore getting an antinode at both ends. And therefore, my wavelength is 2 times the length of the air column, right? If I want a full wavelength, when the wavelength is this big, I just have to double the air column. Okay, so that gets us wavelength is equal to 2L, And then again, if we use the fact that frequency is velocity of the wave divided by the wavelength, but again, here I'm going to substitute this in for the wavelength, I get velocity divided by 2L. Okay, let's do this for the second harmonic, because we can get this for every harmonic now, because that's just how many waves we can get. So of course, here we have one full wavelength. Okay, so here the length is equal to what? This is a special one where the length is actually equal to the wavelength, and the wavelength is equal to L. So really, this is a nice one for frequency, and that's just where you do velocity divided by L, which is the same as the wavelength. Okay? And then we have our third harmonic. So again, what's the length of this guy? So how many wavelengths was it again? Let's count. So there is one full wavelength plus an extra half. Okay, so it's 1.5 wavelengths, which is the same as 3 halves. Okay, so that's our length of this column would be 3 halves of the wavelength, or the wavelength would be 2/3 of the length of the column. And so again, if I want to find the frequency in terms of velocity divided by wavelength, then that would be 3v divided by 2L, because again, we're taking this in, but substituting it into the denominator, and then you do some rearranging so you don't have a fraction and a fraction, and we get that. So can you see a pattern? This one isn't as easy, because here, if we look at our first harmonic, second harmonic, third harmonic, really the third doesn't show up till like right there. Okay, I guess the first is here because we don't really write one. So there we go. And then we have the third here, and again, the first here, but it doesn't really show up in this one. So why not? Why is that? Oh, and then we're dividing by 2 in these ones, but not in this guy. Why is that? Remember, so we are still technically working with halves of wavelengths, but the nice thing about halves is when you divide 2 by 2 or 4 by 2 or 6 by 2 or 8 by 2, you just get a whole number, right? But what do we really have? We technically have 2 halves of a wavelength here. There's 1 half, right? And there's the other half. So 2 halves of a wavelength, well, we just call that 1 wavelength, right? And then so technically we do have 2/2 lengths. But again, why would we put it that way? Okay, and same thing here, it could be 2/2 here as well. So we are still dealing with halves, but then we'll see for every even number harmonic, we'll end up getting whole numbers, which is pretty nice actually, okay? So the harmonic could still go here, because I know that's the second harmonic, but then I just also need to put the 2 in the bottom, because then I need to put it back to a half. Okay, so this one isn't quite as easy, but it actually is, because the thing is, if we always have 2L here, or 2 on the bottom of this fraction, so if we always have the 2 here, then that just means that you need to put in your even number harmonic up there. Okay, and so it does actually end up being 2L down here. So it's, I know, not as easy to see the pattern, but you do get it, and so therefore we can go into a general formula, which is this, is that the length is n times lambda divided by 2, which then you can switch around to be that the wavelength is 2 times the length of the air column divided by n. Again, n is what? It's the number harmonic you're working with, okay? And then of course we still have these, but again, we have the 2L here, and then our fundamental frequency is always related to the frequency at the nth harmonic by multiplying n, the number harmonic, by the fundamental frequency, okay? So again, this is for open air columns. And you know you're working with open air columns if we're working in halves. Okay, or dividing by 2 or multiplying by 2 or something like that, right? If we have those 2's there, that's open air columns. Quarters or 4's is closed air columns. Oh my goodness, I just drew so much here. Gotta go all the way back here. There we go. So here we got our 4's, right? There, and there. So that's gonna be always for closed air columns. So those are always quarters. And your open air columns are always working with halves, okay? So again, other physics classes sometimes don't give you these equations. You just have to figure them out. So you're welcome. So this is just, don't let this, freak you out. This is just, I just wanted to include this so you could see what like all the different harmonics look like for closed and open air columns. Okay, so for closed air columns, remember we can only get the odd numbers, so the first, the third, the fifth, the seventh, the ninth, so on and so forth. Okay, and that's what those look like. So if we have the ninth harmonic, we actually have 4.5 waves, which is half of 9. If we're at the seventh harmonic, we actually have 3.5 standing waves, which is half, right? So it's always half as much. So this is just how air columns work with our harmonics, because it's just how it works. So it's always kind of like half of that. So it's not the same as strings where the harmonic was the same as the amount of standing waves inside there, okay? But the first harmonic, we have kind of like a full standing wave, but it's just in 2 different parts. And then second harmonic, we do have one full one and like 2 halves on each side, so it technically is 2. The third harmonic, we have 2 full ones and then 2 halves, so it technically is 3. Fourth harmonic, we have 3 full ones plus 2 halves, so it technically is 4. And the fifth harmonic, we have 4 plus 2 halves, which is 5, right? So that's how we can tell our different harmonics with air columns. Okay, so yeah, complicated enough for you? I know, but hey, it's cool because this is just how music works. So I just think that's cool. So remember, if you do like to relate this back to like your real world, this is kind of like the clarinet, okay? With the closed air columns, and your open air column is more like a flute, where you do kind of cover the one open end with your mouth, but it's still pretty open. But with the clarinet, with the reed, like you completely close that. So that is a closed air column. A flute is an open air column, okay? So is it more difficult to play the clarinet than the flute? I don't know. I haven't played either of them. I played alto saxophone in high school band, but it's been a long time, so no clue. So let's do an example so I can then stop talking and you don't have to listen to me anymore. Okay, we have an open air column. Okay, that's really important. So open air, we'll go back and look at our equations for open air columns. But again, remember, open air means it resonates at all frequencies. Okay, so an open air column produces consecutive resonant frequencies at column lengths of 14.6 and 20.3. If the speed of sound is 342 meters per second, determine the frequency of the source. Okay, well, we kind of have the column lengths here, right? But we have 2 different ones and we have 2 consecutive things. So here's the weird thing about this. So I have no idea. So this is an open air column. So say this is the 14.6 centimeters. I have no idea how many waves are happening here, right? This could be a lot of waves as long as it's ending on an open wave, right? So that's the whole thing, is it doesn't actually tell me how many standing waves or what frequency or harmonic I'm at. So at first it looks like it's like a big problem. So I'm just gonna like basically draw this until I'm like out of, there we go. So I'll just kind of draw it like that and pretend that that's it. I don't know if that's what's really going on, but let's say that's 14.6. So here's my question. We know the next one happens at 20.3. Okay, so if this is the 20.3 centimeters, it says these air columns produces consecutive resonant frequencies. So what the heck does that mean? What that means is that this will look exactly the same as the one before, except for it will just have that one extra half of a wavelength. That's what it means where it's consecutive. It means that when they change the length to anywhere in between here, from this guy to this guy, there was no sound or very little sound. It wasn't like a nice resonant frequency. That's what it means. If you chop off the end to be like right here, it just means it won't give you a nice sound, or it'll give you no sound at all. That's why the keys are like at very specific places on wind instruments, because they have to be, because those are the lengths that you can kind of close that air column to have a nice resonant frequency. So I know it's a lot, but basically what is this saying? It's just saying that I know that this is the difference between one and consecutive frequency in the next, and so I know that this has to be 1/2 of a wavelength here. Okay, that's all I know. So this is basically the same as saying that this is one full harmonic. Does that kind of make sense? It's a little bit difficult, but remember, consecutive means that there was no way that it resonated in between these two lengths. It only resonated at 14.6 and 20.3. So that means that I know that in between those two, we had two consecutive things, and there's no other way that we could cut this off and have an antinote at the end, right? It was only at 14.6 and 20.3. So if I'm looking to get my length here of the pipe, well, again, I don't know how many waves are in here. It could have been like that, but it could have been way different, right? So I know the length for the first harmonic, at least. If I wanted that, I can just subtract them. I can do 20.3 minus 14.6, and I know that that's going to give me the length that I would need for at least the first harmonic. Okay, so that might not be super intuitive to you, so maybe just think about that. Go back to my explanation once more. But I promise you, if you just reason it out for long enough, it will eventually be like, it'll hit you. You'll be like, oh, so this is the length that corresponds with the first harmonic. Okay? Because again, it's the change between the two consecutive resonant frequencies. And that's what I know. So again, I'm given the length of each column here, but I'm not given what harmonic they're at. So that would have really run into a problem there. So therefore, again, because I always need the length that's corresponding with whatever harmonic we're at, and we didn't know which harmonic this one was at, we didn't know which harmonic that one was at, but I know the difference between them must be giving me one full harmonic, okay? Because it would be 1/2 of a wavelength. Okay, so there's the length for the first harmonic. So again, N is 1, and what are we looking for again? We're looking for the frequency, so let's go back to our equations for open air columns. So here's my frequency is N, number of harmonic, times the velocity divided by 2L. Okay, so now I have all this, considering that I found the length of column needed for the first harmonic, which is 5.7. Okay, oh, let's not use that. So again, frequency, you're gonna N times V divided by 2L. Okay, N here is 1. The velocity of sound here, 342 meters per second. For the speed, really, we don't care about velocity. And then the length, again, for that first harmonic was 5.7 centimeters. What the heck am I doing? Do I want centimeters? Of course I do not. I want meters, because my speed is in meters per second, so that's 0.057 meters. So let's make sure we do that. And then we will get our correct frequency, which I'm going to have to write one down from that. And my frequency is, how many significant digits do I want? I want 3. So that is 3.00 times 10 to the 3 hertz. Okay? So that's just an example of a slightly more difficult question I could ask if I didn't actually give you the length corresponding with the frequency, a known frequency. Then if you ever see this word consecutive, then you know, oh, I have to subtract them, and that's giving me the length for the first harmonic. Okay? So that's that. Those are air columns. Now you know how music works. Isn't that exciting? Well, you don't fully know because now you don't really know how sound travels through the air, and that's what we're going to learn in the next video. I know you're so excited and you're going to watch it right now, but don't worry. Just do the workbook questions for this first. Okay? Bye.